Let's talk about vector properties. Suppose I have a vector v, and I want to shrink it by 1/2. I don't want to change the orientation, I just want to make it shorter. While if I want to double it, I again don't want to change the orientation, I just want to change how long it is. So scalar multiplication is just stretching or shrinking a vector. And we can find those components by multiplying the components themselves by the scaling factor. Now that's not true if we're going to add vectors. If I'm adding the vectors v and u, the easiest way to do that is to add the x component of v to the x component of u, and the y component of v to the y component of u. And this is a much easier form than a lot of the other vector additions you've done in the past. If you're going to subtract u minus v, then you start with u and think of it as adding a negative v right here. So u minus v is the same thing as u plus negative v. Now, here's just a summary of the rules we just went through. And if you look at the properties of vector operations, you can see we have the commutative property, we have the associative property, the additive identity, and the additive inverse properties. It doesn't matter how you group the constants out front. The distributive property works whether you're distributing constants over one vector or a constant over two vectors. And of course, we have the unit and zero vectors there. The length of a scalar multiple, if I scale my vector like we were doing when we first started, then all I need to do is take the magnitude of the constant and multiply that by the length of the vector. Now, this is a really cool inequality that says if I add two vectors, u and v, it is going to be less than or equal to the length of u plus the length of v. And you've done this, you've been doing this in trig and in your mathematical career all along. The only time these two are equal, of course, is when these two, u and v, are actually parallel. Now, suppose I have v is negative 2, 5, and w is 3, 4. Let's say we do this one right here, because that one's pretty easy. W minus v. All right, the easiest way to do this, we're going to start here with w, and we're going to subtract this term. So this is 3 minus negative 2, 4 minus 5. So this is, let's see, 5, negative 1. To do something like c, v plus 2w, the easiest way to do this is negative 2, 5, plus, now I'm going to go on and double this one in here, 6, 8. So when I add these, it's 4, 13. That's kind of the shortcut I do in my head when I'm doing these problems. Suppose I have a vector whose magnitude is 3 and makes an angle of pi/6 with the positive x-axis. Write v as a linear combination of the unit vectors of I and j. Well, let's see. This is another notation that we use. So if I have vx, vy written this way, we use the ijk notation, which is, if this is v, then v can also be written vx, I, where this is the unit vector in the I direction, plus vy times the unit vector in the j direction. Now, I have to put hats on them because I can't do the bolding. All right, so the magnitude is 3 and the angle is pi/6. So let me look at my x component. That's going to be 3 times the cosine of 30. The y component is going to be 3 sine 30. So rewriting this, I get, lost my pen, v is equal to the x component, which is 3 root 3 over 2, I, plus 3, nothing else,